This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Week 3, Lesson 3. Compressor work, volumetric flow, and displacement. The compressor is the one place work enters the refrigeration cycle. Its power is just the enthalpy rise across it. Mass flow times H2 minus H1. Its physical size comes from the suction volume it has to swallow every minute. Mass flow times the suction-specific volume. And isentropic efficiency turns the ideal work into the real shaft work. We'll ground all three, then size 1 R22 compressor per ton, and check every answer against the handbook table. Concept 1. The compressor adds the work. It's the only place work enters the cycle. So on an adiabatic compressor, the energy balance gives the work as the enthalpy rise. Mass flow times H2 minus H1, with the enthalpies read straight off the pH chart. There's also a temperature form, work equals minus Cp times the temperature rise. But that's for an ideal gas like an air compressor. For a refrigerant vapor, use the enthalpies. Concept 2. Isentropic efficiency. The ideal compression follows a line of constant entropy. A real machine runs hotter and takes more work. Efficiency is the isentropic work over the actual work. So the actual work is the ideal work divided by the efficiency. You divide, so a lower efficiency means more work, never less. For an ideal gas, the same ratio becomes the temperature form. The handbook also prints closed-form adiabatic and isothermal power, both carrying the efficiency, but with the enthalpies on the chart, you rarely need them. Concept 3. Volumetric flow and displacement. A compressor is really a volume pump. It has to swallow the actual volume of low-pressure suction vapor each minute. That's mass flow times the suction-specific volume. And you must use the suction value, state 1, where the pressure is low and the specific volume is large. At 100% volumetric efficiency, that volume flow is the compressor displacement, and the per-ton comparison table lists it directly. A real machine needs a bit more displacement to cover volumetric losses, but that efficiency isn't a printed curve. Setup. An R22 compressor sized per ton. 1 ton of refrigeration, saturated cycle, evaporating at 20 degrees and condensing at 86. Off the R22 chart and table, suction enthalpy 106.5, isentropic discharge about 118.5, saturated liquid leaving the condenser 35.2, and a suction-specific volume of 0.935 cubic feet per pound. The real compressor runs at 80% isentropic efficiency. The plan: get the mass flow from the refrigerating effect, then the work, the volume flow, and the real work. Solve. Part 1. The refrigerating effect is 106.5 minus 35.2, 71.3. Mass flow per ton is 200 over that, 2.8 pounds a minute. Ideal work is mass flow times the 12 BTU enthalpy rise, 33.6 BTU a minute, which converts to about 0.8 of a horsepower per ton. The handbook table lists 0.772. Our chart read lands right on it. Solve. Part 2. The suction volume flow is mass flow times the suction-specific volume, 2.62 cubic feet a minute per ton. That matches the table's compressor displacement exactly, because that column is nothing more than mass flow times suction volume at ideal conditions. For the real work, divide the ideal 12 BTU work by the 80% efficiency to get 15, so the real duty rises to about 99 hundredths of a horsepower per ton. Traps. 5 ways this bites. 1. The work is discharge minus suction enthalpy, H2 minus H1, not H2 minus H3, which is the condenser heat rejection. 2. The temperature form is ideal gas only. For a refrigerant, read the enthalpies. 3. Efficiency divides. A lower efficiency means more work, so never multiply. 4. Use the suction-specific volume in the volume flow. Grabbing the liquid or discharge value collapses it. 5. Displacement is at 100% volumetric efficiency. A real machine needs more. Quick recall. Work is the enthalpy rise, mass flow times H2 minus H1, with the gas form as the ideal gas alternative. Efficiency is isentropic over actual work. Mass flow comes from the refrigerating effect, H1 minus H4. Volume flow is mass flow times the suction-specific volume, and that equals the ideal displacement. Golden rule: mass flow rides on the refrigerating effect, work on the enthalpy rise, volume on the suction-specific volume. Next up, Lesson 4, Multi-Stage and Cascade Systems. One compressor spans the whole lift here. When the pressure ratio gets large, we split it. Lesson 4 builds the Handbook's drawn two-stage cycle, dual compression, dual expansion with a flash intercooler, where the total work is smallest when the stages share the compression ratio equally, and it closes with true cascade as a named concept. Everything's at peprepengine.com. Cheat sheet, work solution, and a quiz attached here. If the course helps, subscribe.
The full study guide with every equation and common exam trap is free at peprepengine.com, link in the description. Structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.